Um, Everyone see my screen right now?
Yep.
Yeah.
Okay, cool. I won't be able to see you guys, but if you have any questions, feel free to just interrupt me. I'll be glad to answer them. Okay, so this is the CNC manufacturing workshop. I'm just gonna go over some basics. All good stuff to know before you go into CAM, where you start to program the CNC machine. I think it's a good idea to have the fundamentals first before you start programming. So, first of all, what is CNC? It's pretty much any sort of machine that's controlled by a computer, and typically those machines are used for making mechanical parts. Like for our purposes, we're going to use a lot of aluminum, sometimes carbon fiber, but they're all going to be made from CNC machines, and they're all going to be coded by a computer to run the machine. So I think recently we've been using a lot of laser cutting because we just have that available. But we also have a water jet available. We don't really have a plasma cutter or a CNC router available. But in the future, we'll be using a lot of the mills and lathe inside of Washburn. So I'm going to be talking mostly about the mill and lathe because those are a little bit more advanced and a lot harder to use. So let's get started. So for typically parts that are 2D extrusions where everything is the same thickness, you can get away with one of these three machines, the laser cutter, water jet, or the plasma cutter. The only difference is the type of material they can cut and the thickness. So typical wood, acrylic, paper, you typically want to stay away from like laminated wood because then they can create some weird gases that are not safe. But wood is really good for laser cutting. Difference between water jet and plasma cutter is the thickness that you're allowed to cut. Plasma cutter is really good with just cutting really thin sheet metal, but if you want something thicker like 1/4 inch or more, then you're really going to want to go to water jet because the water jet is able to cut thicker parts, thicker metal. So we don't really have access to a good water jet right now, so we'll have to stick with using either a mill or a lathe when we're trying to cut like thicker aluminum or steel. For parts that are not just 2D extrusions, where you have multiple bosses, you're gonna have to use a mill or a lathe. But for the most part, you can just use a mill. You can make parts with multiple bosses, bunch of holes. The holes can be tapped. You can put a bunch of chamfers on them. So the mill has very high like capabilities and make a whole bunch of parts. You just have to know how to use the machine, and you can make a lot of very advanced parts with the machine. Here's some of the parts here's the Lathe plate that we made last year. Here's brackets that we made last year, and these other two parts are just stuff that I found on the internet, but they're all can be made on the mill. And here are some parts that can be made on the lathe. So typically the difference is that the lathe spins the part while the mill spins the tool. That's the main difference. And because the lathe spins the part, you're able to make parts with a cylindrical like profile. So any cut that you make on one side will be projected onto all 360 degrees of that part. So you're able to make symmetrical parts about the same axis. You can put threads on it. You can put a bunch of grooves. Here's a bolt that was made earlier this year. Here's the couplings that were made, and this is one of the shafts that Payload made last year. All made on the lathe, but they look very different, but they can be made with the same machine. And so for CNC machining or any machining, there's something we have it's called stock, which is just that raw material that we're going to use to create a part. So with most CNC machining, it's called a process called subtractive manufacturing, where you have the material that's more than what your part is, and then you cut into it to create it. While like something like 3D printing or resin printing is quite the opposite because you just have nothing and then you build onto it into the final part. But these are the main type of stock that you can buy. That the typical plate or block stock, it just looks like a rectangle. Then you have your flat bar stock, which is very similar to your plate or block stock, but it's notoriously known for like being longer, so you can make a bunch of the same part, multiple parts on the same stock. And those two are really good for fixturing inside of a mill because mills really likes rectangular parts. And then you can get tube stock or bar stock, they're circular, so they fit really well inside of a lathe. So these are your like main four options. We're probably gonna stick with mostly that like plate stock because we're gonna make a bunch of like bulkheads which are relatively flat. So we don't need really thick parts. And if you're gonna do anything in the lathe, then we're probably gonna go with bar stock. You're gonna want to go with tube stock if you want to reduce machining time because it takes time to remove material on the inside of that bar stock. So you can just buy it like drilled out. So it saves a little bit of time. So we're gonna go first into the mill, and then we're gonna talk about the lathe afterwards. So for the mill, these are the main tools that you're gonna be using for the most part. There's a lot of other like strange tools to make like interesting features, but for our applications, if you use these 6 tools, you'll be able to get like almost everything you're gonna want to use. So we have a face mill, an end mill, a ball end mill, a chamfer mill, a drill, and a tap. They can be used for like all different type of things, but they're good at certain things and bad at certain things. But in the bullet points, there are the type of cutting operations that you can do with these type of tools. So cutting operations are essentially the processes that the CNC machine does. And they all remove material just in different fashions in different places. But over time, you're going to get familiar with the terminology, and it's important to actually know what everything is called, so it's good to communicate. First, we're going to talk about facing. I just made a quick little animation of what facing is. It's pretty self-explanatory. It kind of is described in its name. When you want to do facing, you can either use a face mill or an end mill. Face mill is preferred because it has a really big surface area, so it's able to like cut a lot of material really fast. Plus, since it's cutting like it's taking less passes, it takes less time to cut, so the surface finish is going to be better. You can do the same thing with an end mill. It's flat, similar to a face mill, but its surface area is not that big, so it's going to take a long time, and then your surface finish may not be that good. But use a face mill. You'll save a lot of time. So the purpose of facing is typically to remove that top surface because when you buy stock, it looks flat, but like for making high tolerance parts, you want to have like everything as flat as possible. So there will be some surface roughness on stock when you buy it, but if you face it, then you get super clean. You remove the oxide layer, and that's typically what you want to work with. Everything in your part should be clean, and nothing should have any oxidation on the outside. Yeah. Next, we have contouring. You can also use either an end mill or face mill. Face mill is not ideal because that's so much surface area, it's not able to get into those small little grooves. Like for this application, face mill is fine because we're just making a circle. It's just cutting on the outside, and it's able to create that outer profile of the part that you're going to want to make. Then we have pocketing, which is just the opposite of contouring. You're going to want to use end mill because the face mill is too big for most type of pockets that you want to make, since it's so massive. End mill is good for also getting into those nooks and crannies. Yeah, and it's the opposite. It just creates the inner profile of a part, so you can create nice little holes and pockets inside your part that way. And we have chamfering. So there's this nice, neat little tool called a chamfer mill. It's really good for chamfering, but it also does a lot of stuff. But for chamfering, it just creates 45-degree angles and edges, which is really nice because when you cut right corners into aluminum, it's very sharp. I can tell you from experience, it will make you bleed a lot. So to make sure to put chamfers onto your parts, it's easier to hold the part. It's safer when you're like touching it. Also looks nicer. But yes, please add chamfers into all your designs so we can make sure we don't hurt ourselves. Next, we have a spot and drill. So the chamfer mill is able to make chamfers, but it's also to do something called a spot, which is something you do before you drill into your stock. So it puts a little dent like these, into your stock, and it just helps lead in the drill. So once it has like a little dent into it, the drill is able to find that hole really easily. For really slender drills, if you don't have a spot, it's likely to deflect because it's not strong in that direction, so it will deflect. But having a spot really helps, and it's worth the time to program and put into the machine. So you should always put a spot and then a drill afterwards. Plus, if you're also already doing chamfers, you might as well just put spots into your program as well. It doesn't add too much time. Yeah, so it's really good. In here we have tapping. So if you want to make any sort of threaded holes, internal threaded holes, and you want to use a tap, there's two types of taps. There's a form tap and a cut tap. In Washburn, you mostly have form taps. The difference is that a form tap doesn't cut material. It just like pushes material away. Like it kind of just like mushes everything into a place, while a cut tap is actually removing material. So if you look in this video, you can definitely tell it's a cut tap because you can see like aluminum or whatever this material is actually coming off. And it's steaming, so it's like definitely needs some coolant or something. So that's not really good. But before you tap, you want to make sure you have a hole. You can't just tap into the material when there's no hole. So like before you drill, you want to spot. Then you want to choose the right drill. So you can't just choose any drill when you want to tap, because every thread type has like a specified major diameter or minor diameter. So if you use the right drill to get that ideal tap. So so there's something called tap drills, which is just the ideal drill you want to use before you tap the hole. And then for most part, we're going to be using 1/4-20s and 8/32s. And since we use form taps, you want to have number 1 drills and number 25 drills handy. So if you want to make a number 8/32, then you're going to spot, then you're going to drill with a number 25 drill, and then you're going to tap with the number 8 tap. There's a separate tap for each type of pitch. There are also metric taps, but you'll have to search up what those are, because I think Payload uses some metric taps, and Air Brakes is probably using some metric taps. So you'll have to search up what the ideal tap drill is for that. But these are pretty much the 2 taps we've used a lot in the past, so I just have those memorized. Yeah, so okay, so now we went over all the tools that you could use in a mill. Now we're going to talk about cutting parameters, and essentially these are numbers that you put into the program, and it pretty much controls how the cut is made. So 2 main things is what you call feeds and speeds. Speed being your rotational speed, and feed being how fast you're moving in each planar direction. So typically when you think about speed for something that's spinning, you go straight to RPM, because it's just something that's easy to conceptualize. But for machining purposes, it's more important to think about SFM, which is surface foot per minute, which is just the tangential speed of the outside of the tool. But that can be easily converted between RPM and SFM. But we're not too worried about the RPM, because FSM tells us how fast the tool is moving with respect to the material. So it gives us some information, and depending on the tool you're using and the type of material you're cutting, your feed and speed will change. But those numbers are well documented, so you can search them up. And then we have feed. So we have 2 types of feed: XY feed and Z feed. You can imagine XY feed as just how fast the tool is moving in like that XY plane, which is just the flat plane, and then Z being how fast it moves up and down. So you have different units. There's inches per revolution, typically used for drills, and you have inches per tooth per revolution, which is used for other tools, and then they can be converted into inches per minute. You shouldn't be too worried about converting them, because Esprit, the program we're using, and almost all other CAM programs, they automatically convert it for you, so you don't really have to worry about converting these numbers. And here's an animation of just way to conceptualize what is low feed and what's high feed. Yeah. Next we have depth of cut, which is our 2 our last two cutting parameters. So we first talked about speeds and speeds, and then we have two types of depth of cut. We have radial depth of cut, and we have axial depth of cut. Radial is pretty much the direction pointing away from the center of the tool, so how deep you're moving into the material, while axial, how deep you're going down into material. And there are ideal numbers. These numbers aren't really set in place. You kind of can pick your own numbers. Although there are ideal ones, you can cut more material faster if you increase your depth of cut. So for radial depth of cut, it's recommended that you go 20%, 20% of your diameter. So if you have like a 1/2 inch end mill, then every time you pass through the material, you want to only go in 20% of your 1/2 inch every single pass. You can go higher and higher. The higher your depth of cut, the faster you remove material, but then you're also putting a lot more force onto your tool, and therefore your tool is going to wear down faster. And also, once you pass a certain threshold of depth of cut, you can possibly break your tool. Same for axial depth of cut. They like pretty much. I know a lot of like high production, like machining companies. They use like really aggressive depth of cut because they have to make money fast. So they're trying to make their parts as fast as possible. But for our purposes, we don't want to go crazy on how fast we make our parts because it becomes a lot more dangerous when you start breaking tools. And we're not too worried about how fast we can make our parts since we're all just learning. It's okay, just have a less aggressive tool path. So stick with 20% diameter radial depth cut, and then for axial, you want to stick with 1 diameter's worth. So if you're using 1/2 inch end mill, then you want to go 1/2 inch down per pass. And those are just kind of recommendations. They're not numbers that are set in stone. And that's the same with speeds and speeds. So there's an ideal number because the manufacturer tests the tools that they make, and they kind of tell you, oh, this is like the tool operates the most efficient way during these speeds and speeds. But you can change them to your liking. Just the more you deviate from the ideal number, your likelihood of breaking the tool is significantly increasing. But if you kind of use that tool a lot and you have an intuition of the limits that the tool has, then you feel free to change those numbers as you want. But good place to start with those documented numbers because they can't go wrong. So yeah, we have 4 cutting parameters: speeds, radial depth of cut, and axial depth of cut. So those are your 4 important cutting parameters. And luckily for us, Washburn has documented most of these speeds and depth of cut on their website. So if you go to wpi.mfelabs.org, you can just find them. So we have milling tools and you have lathe tools. All have every tool with the respective material class has their own feeds and speeds. So we're mostly going to be cutting out of aluminum 661, and that is class N2. So there's a lot of different classes like M1 or whatever, but some of them are like steel, some of them are like different plastics, but for aluminum 661, you're going to go with N2. Okay. So there's a good amount of limitations with what a mill can make. It's definitely a very powerful tool, but there's so many things you can do with it. One thing it really does not like is right corners. Any type of right corner or sharp corner, it cannot make. So imagine you're trying to make this part. Just put something really quick in SolidWorks. It's not anything useful, but it has a ton of really sharp corners, and because an end mill is a circular shape, it's not able to make those infinitesimally small cuts. If you have an end mill with like a very, very, very small diameter, it can't cut it, but it will still add a little fillet to it because all of our tools are circles and you can't make a corner with a circle. So you'll end up getting fillets on every corner you get. If you really need those right corners, then a mill is not the right tool to use. There's other tools that can make right corners. Mills is not one of them. But if it's okay that you leave right corners, then the CAM program will just try its best to cut as much material as it can and it'll just leave the rest. But you can clearly see like it does not cut all the way. but it tries its best. If you're trying to put two parts and mate them together with high tolerance, like this one, so if we look at the top right, there's this red part that has a nice pocket in it, and it's supposed to have that green square fit into it, like perfectly. So you would expect it to just, all the corners line up. But that's not the case because internal right corners cannot be milled, and you'll end up getting these fillets, and therefore the part can't actually fit in there. But a nice little solution is if you can add these little smaller pockets to relieve the corners called dog bones. Then you're able to actually fit that part in. It's not very aesthetic, and if your part is very has a lot of structural importance to whatever you're making, then maybe adding a dog bone is not the right way of going about it because you're removing material. You have no idea how it affects the strength of your part. So you want to be careful if it's a structural part, but if it's not structural, then you go ahead and add as many dog bones as you want. Yeah, that's how you can. That's one of the solutions. It doesn't look very nice, but it gets the job done. Also, we have the tools are circles, but there are even more circles on the tool. So on the corners, if you look at here, there's nice little fillets. They're not as big as the red lines that I've drawn. I'm just making them big because they're kind of small, so I just want to exaggerate it a little bit. But each tool, the corner radius is around typically 10 to 30 thousandths of an inch. So you won't be able to make right corners in that direction either. So if you want two parts to be flush in that right corner, you would expect to be this, but then once you mill it out, you'll have a little corner because all tools have corner radiuses, and you'll have the red part lifting up. And if it's really important that the two parts are flush, then that's going to give you a real issue. But there's ways to get about it. You can mill, you can cut lower into the green part to add a relief channel, so all the fillets are out of the way. There's still fillets, but there's no material there, so you don't really have to worry. Or you can add a fillet or a chamfer to the other part to either match that fillet or make it even bigger, so you can leave a gap in there. But these are all things you should really consider when you're designing stuff. Like if you want two right corners to be flush, that's not possible. So when you're designing, have those type of things in mind. So when it's time for machining, it's actually possible. Because a lot of designs are not they're either not easy to machine or impossible to machine. So yeah. Now we're moving on to the lathe. Lathe, it's a little more tricky. It's a lot more involved. Instead of just choosing your tool, you also have to choose your tool holder. So you have an indexable tool holder and a boring bar. The difference is that the indexable tool holder creates features on the outside of your part, while the boring bar creates features on the inside of your part. So they're just steel tool holders, and they have little gaps to put your inserts. And inserts are those golden things. And you buy them. They're made of typically carbide or sometimes ceramic. And you just bolt them on to a tool holder, and then you combine them, you can make a full tool. So you need an insert plus a tool holder to make a full tool in the lathe. So we have cutting inserts, all different shapes that you can buy. We have boring inserts that are specifically made to put on a boring bar. We have our typical drill, and we have this new thing called a cutoff. Its purpose is to cut parts off of the stock, and then we have a threading insert, which makes threads. Yeah, so with the right combination of tool holder and insert, you can make a tool. So we have facing, very similar to the mill, except it's not with a face mill, it's with an insert. So if you put a cutting insert onto an indexable tool holder, which look like this, you can make a tool. So the tool main inserts we have in Washburn is called the 55 and the 35 insert. 55 being the degree of this corner right here, and 35 being this one. So this slimmer angle and then wider angle here. Either of them work for facing. I think they recommend using the 55 insert. It's totally up to you, but it creates a flat surface for you to work on because stock is rough and it has an oxide layer on it. Yeah, so that's facing. Then we have OD roughing. You can pretty much make like any type of OD profile with an OD roughing toolpath. Same thing using either a 55 or a 35 insert. You'll want to use an indexable tool holder because it's an outer diameter feature. So you'll stick with that tool holder. And then you can just take passes and then create whatever shape you want while it spins the part. And then we have drilling. So self-explanatory. The limitation to a drill in a lathe is that it can only drill in the center. So that's something to look out for. There's different drills you can use. This regular drill bit that the same thing as the one you put into a mill. And then for lathe, there's a special one called an indexable drill. So if you look, there's actually like inserts here, and it's able to cut tougher materials. So yeah, that's two different types of drills, and also like a lot beefier. So you don't have to worry about this breaking as much as this little one. But yeah, they just make holes, which is very neat. And then we have ID roughing, which is same thing as OD roughing, except on the inside of the part. Before you want to put your boring bar, so boring bars is for internal features, so you want to use a boring bar for ID roughing. You want to first drill a hole into your part. Oh, you're going. Okay, like this, yeah. You want to drill a hole first, and then you'll be able to fit the boring bar into the hole so you're able to cut it. If you have a perfectly flat surface, there's no way you're going to be able to put the boring bar into it because it will just crash into the part. So yeah, first want to drill, then put a boring bar inside of it. And you can put any type of insert. There's all different inserts you can put on a boring bar. It's totally up to you. There's some that are more specialized for certain scenarios, but there's a specific boring insert that you can use, and it cuts most of the stuff that you're going to want to do. Then we have threading, both ID and OD threading. So for the couplings people, we've done both. And threading is a little tough because it's different because it has a specific toolpath, and you need to know all like different parameters like pitch. You need to know major diameter and minor diameter. So there's a lot that goes into threading, but the difference between OD and ID threading is the type of tool holder you use. You use an index tool holder, then OD, and if you use a boring bar, is ID. So it's pretty clear in these two pictures, and these are just two nice little images. Yeah, they both do the same thing. They just cut in opposite directions. And then for cutoff, it's very self-explanatory. It just removes the part from the stock. So once you finish cutting all your features out, you can use a cutoff insert, and it just removes the part from the stock, and then you can just make the part again. Yeah, this is pretty much always the last operation that you do, because once the part is off, you can't really cut into it anymore. Yeah. So we just talked about milling and lathe operation. So those are different tools you can use and different type of cuts that you can make. Some really important thing before you program your machine is figuring out how you're going to actually hold your part. When you make more advanced parts, you're probably gonna get like really weird curves, and like it's gonna be really hard to hold on to. If you're making like a square part, like that's really easy because you have a vise like this that you can hold onto. But once you get into more curved parts, then fixturing and work holding becomes a bit of more of a challenge. So for a vise, you have both hard jaws and soft jaws. Hard jaws being made out of steel, they not meant to be cut into. They're just really good at holding squares and rectangles. But if let's say you're making this side apart, which has like really weird curves and edges, you're not going to hold that in that hard jaw. So you can buy these soft jaws, they look exactly like hard jaws, but they're made out of aluminum. So you can cut out a profile into them like this, and then you can fit your part into it. So it hugs your part just perfectly. So sometimes if you make like circular parts, soft jaws are a good thing to consider. We also have fixture plates. Those are also very powerful type of work holding, especially if you make a part with holes inside of them. I know like we did some linkages that we made, like centering rings that we made last year, all had holes in it. So we all of them used fixture plates. So you can see these plates all have like lots of holes into them. And because your part has holes into them, you can just bolt your part onto a fixture plate and it holds it perfectly. So like this one right here, this was our centering ring last year. It was just bolted into a plate and I was able to machine it really easily. And then the three on the left, they're fixtured onto things called toe clamps. The toe clamps, like these things, these black things, they're bolted onto something and then they squeeze your part down. And this one, it seems like it squeezes it down and in at the same time. So pretty neat. So yeah, fixture plates are really good if you need to hold like flat pieces or parts with holes in them. And then the thing on the right here is a pallet that we made, which is very similar to a fixture plate, but is meant for like machining many parts at once. Yeah, it made the radial brackets last year. It made 8 of them at once. So it's really good for like high production manufacturing. But for the things we do this year, we probably won't need one of those. No. So we just talked about metal fixturing. Now we're talking about lathe. Lathe is a lot more simple because you can really only machine circular parts in a lathe. So because of that restriction, it's so much easier to fixture and hold your part. So you have the same thing. You have hard jaws and you have soft jaws. Hard jaws being steel, soft jaws being aluminum that you can machine into. With soft jaws, you can machine stuff that are not circular because you're able to create whatever profile you want into the soft jaws. And that way you can also machine any type of diameter you want, while hard jaws have a range of diameters it can hold on to. Yeah, so very good options for holding circle parts because, you know, very straightforward. You don't have to worry too much about how you're going to hold the part because it's meant for holding circular parts. And then we also have collet chucks, which are, so this is the thing on the inside, it's collet, and it pretty much holds a specific diameter and only that diameter in its own, but it's really good at keeping your part from wobbling. So this collet chuck is probably the most precise method of holding your part, but its limitation is that it can only hold one diameter. But if you buy multiple collets, then you can be able to hold different diameters. But in Washburn, we have a bunch of different collets that go up to around like 1 inch. But anything over 1 inch, then you want to look into hard jaws and soft jaws. But collet chucks are great for really small diameter parts because they're very accurate. Yeah. I have a couple parts that I put together in a slide, and we're gonna talk about like what type of machine you're gonna use, and how you're gonna fixture and how you're gonna actually machine this. So I'm gonna ask you guys. So first of all, are there any questions about the previous slides? And then if not, we're gonna move on to our case studies. Okay. So I'm gonna give you like a few seconds to look at the part and then think about yourself, and then one of you guys can pretty much try to figure out how you're gonna actually machine this. So first, we have this part. This was last year's thrust plate. We're gonna start with an easy part, and we're gonna progressively go into harder parts, and their fixturing methods become a little more abstract and different tools they have to use. So we'll start relatively easy. Does anyone want to give a shot? First of all, what type of machine do you think is a good idea to use? We'll start with that.
I would think the mill is a good machine to use.
Okay. I agree. Why do you think that a lathe is not a good idea?
Because you have to make specific holes on the not in the center, and
Okay.
that's impossible to do in the lathe.
Right. That's right. Even though the part is circular, which is great for a lathe, the features are not symmetrical about the axis, so you're not able to actually make this on a lathe. Yeah, it's great. any ideas on how you're gonna fixture this into the machine? I recommend
I can
opening up
give
the
it.
slides because you
Okay.
can just refer back to past slides.
I have an idea.
Yeah, go ahead.
It'd be probably soft jaws because it's not a square shape or
Yeah,
rectangular shape.
we can definitely make soft jaws. What are some other options?
You could use the clamps.
Yeah, you can totally use clamps. The reason why I prefer clamps over soft jaws is because soft jaws, um, they're expensive. So if you're trying to make one part, like if you can avoid using soft jaws, that'd be ideal. If you want to make like a ton of the same part, then soft jaws is great because it's very fast. But it also costs money to make. While clamps, we already have all of those. You might as well just use them. But soft jaws, they really only fit one profile. And once you make it, there's no other part that can use that soft jaw. But soft jaws are totally a reasonable method of holding this part. You can use clamps. So for last year, we used a combination of clamps and a fixture plate. Because we have holes, we're able to bolt them into a fixture plate. So that worked really well last year. Okay, so what type of tools and what type of tool paths would you use? Actually, first of all, what type of stock would you recommend that we would buy to make this?
We just like cylindrical.
We could. You can get a cylindrical stock. We totally can. We didn't last year, mainly because cylindrical stock is a lot more expensive than rectangular stock. We totally can make this out of a cylinder. Yeah. Okay. So let's say we did use cylindrical stock. What type of tools would you use to cut this?
Probably start with facing, then drill, and then I would do some boring, I think, right?
So yeah, definitely facing first. You can heavily tell like the top was faced. Then drilling, you have a bunch of holes. You have 8 holes on the outside, then you have 1 hole in the center. How would you make these pockets here? You have 4 of them. What type of tool would you use?
Would you use an end mill?
Yeah, totally use an end mill. That's pretty much the only tool you kind of would use. And then what about that? You said big chamfer. What are some ways that you can actually make that?
That's the chamfer, right?
Yeah, the one right here,
Yeah.
the countersink for the hole. Yeah, what type of tools could you use? Any ideas? Um, so you can probably use a chamfer mill, but I think last year what was done was we found this like big chamfer that like was able to just drill into it and it made that profile, so that was pretty neat. So there's a lot of different tools that you can use, not just outside of the 6 that I've shown you guys. There are a lot of different options. But yeah, this part relatively simple to make, not too crazy in terms of fixturing. So we're gonna move on to the next part. It's gonna get a bit harder. First, what type of stock would you buy, and what type of machine you're gonna use?
I would personally get cylindrical stock and use a lathe.
Okay. Yeah, you would definitely use a lathe for this part. Some bar stock would be great. What type of tools would you have to use to make this? So we have a nice bore over here. We can either use a drill that matches that exact diameter, or we can use a smaller drill and then bore it out with a boring bar. We have a lot of OD features, so you can just use a cutting insert. So that would create that pattern profile. Then you also have some little grooves here. Not really sure what they're for. They could be for like O-rings, some snap rings, who knows. But you can use a grooving insert, or you can just use a cutoff insert. A lot of different options that you can do. One part of the piece that really concerns me, that these holes, definitely cannot make them in a lathe. So what other options do we have? Feel free to give it a shot. Don't be scared.
Put it in a lathe first, and then afterwards mill it.
Yeah, totally. That's how I would do it. Yeah. How would you fixture this?
I put a bolt through that center hole. Then
Okay.
maybe try to drill. Not sure how that would go.
Yeah, I think that could work. I'd be concerned about how big that bolt is going to be, because I assume these are like kind of standard, maybe like 832s or number 6 bolt holes or something. This would be a really big hole. It'd be a little difficult to bolt in. It's possible. What other methods can we use? Well, we can use clamps that hold onto the bottom of it. Then we can drill onto these. And we'll probably have to flip it around to drill these holes on the opposite side. It seems like this flange kind of overlaps these holes, so you can't just drill all the way through. So you'll have to flip it again afterwards. So it's a little more tricky, but only lathe one time and 2 different programs in a mill. So 3 different operations.
Are there no drills that can go kind of all the way through? I guess. Oh, actually, I guess the holes don't line up.
They can. Yeah, it did not look like the holes lined up, which is why you would have
There's
to.
a different number of them.
There's also different. Yeah, exactly. There's also a different number of holes. So yeah, you'll have to drill opposite sides, but you know you can figure out a way. Now we have this part getting a little bit more complex. Let's figure out what machine, what type of stuff we're going to use. We'll start with that. Let's think. Would we use a mill or a lathe?
you're going to use a mill for, I guess first you're going to start with the face with the big hole in it, the biggest hole, and then you're going to have to flip it around to do the face with, I guess, that tapped hole on top and the two on the side.
Yeah. So you'll definitely throw this in a mill. You'll cut this front surface, then you'll rotate it 90 degrees to add this tapped hole. Then this, a little tricky. It's on an odd angle. There's really no good way to fixture this. You can probably just throw it onto a vise, indicate it until this surface is like flat, perfectly level, and then you can cut it off from there. Yeah, so one machine, 3 different operations. Well, technically 4, because I assume there is another hole on the other side. So if there is, then you need to do 4 different programs, but on the same machine. It's definitely doable. It's a little tricky to fixture. It's also great that there's holes here. So once, actually no. Question is, how would you fixture this when you try to make these 3 holes? You definitely just put in a vise. Yeah, you throw in a vise.
I have a question.
Yeah.
Would you do those angled, like 45-degree angle holes first, just because they had like the highest risk of failing in whatever way, or would you do them last, or does it matter?
So I think you would do them last.
All right.
Because when your first operation would be cutting this front face, right? And then you would remove all this material on the outside. So you would get this perfect profile here with this 45-degree angle. So the only issue is, how can we make sure this surface is flat when we're cutting into this hole? It's definitely doable. There's tools that you can use to make sure the surface is flat, but there's no like perfect method of fixturing this. At least I don't think.
Oh,
At least not a method that's worth the money or time.
that makes sense.
Okay. And then we have our last part. This one, oddly shaped. I'd be scared to make this too. But first of all, which machine? And then what type of stock?
I would go with a mill
Mm-hmm.
and just use like bar stock.
Yeah, that's probably a good idea. It's like really long, so you can make this out of a bar stock. Yeah, totally. That's a great idea. So first operation, you throw onto a vise because it's a bar stock. Vise love those. How would you make that? Like, how would you go about making this?
I would cut that big hole first,
Okay.
and then assuming it's small enough to put a screw through, screw it down to a fixture board, and
Okay.
then cut all the material away.
Okay.
And then hope that works.
So what problems could you potentially like encounter if you're bolting at one place? If you're bolting here, you're restricting the part's motion in only one direction. So it won't move up and down, but it can totally rotate, which could be a big problem because when you're cutting to this, the part is going to want to move. So how could we get this part to not rotate? Let's say we do bolt it in somehow on this hole. Like what way can we stop this part of the part from like flipping over?
Possible idea I have is like you would have extra material on the left-hand side and just clamp it down over there. That's
Yeah,
all.
you can definitely do that. Actually, that'd probably be a really good idea. I think for this part, because of how complex it is, it might be worth to make soft draws because everything is so oddly angled and there's curves everywhere. You're probably saving more time and you're not going to go crazy over fixturing. So maybe soft draws would be the right way. You also have this hole on top, which is another issue you have to deal with. So maybe fixturing with a soft draw is probably the easiest way of doing it. Yeah. So yeah, that is our last part. So that is it for our CNC workshop. I'm just opening up to any questions now. Could be a question generally about CNC, or maybe a specific part that you plan on machining this year. Anything.
What software do we need to have on our computers so we can program the CNC machines?
Okay, so software called Esprit. If you go into our SharePoint, go to Files, then our software, then this Esprit download file is here. Because we're not on the school VPN, it's annoying to get it. But if you go to API Esprit, there are download instructions. If you click on install guide, there's all instructions. But since I have the download file here in the Esprit.zip folder, you can just skip to step 3. Yeah, and then for each whatever machine you're using, you want to make sure you have the right template. So I also have a lot of additional files that I've put on here. So if you go to File Templates, there's a different template you want to use for each machine. So we have SD. These two middle ones are both lathe, and then this mill. So yeah, you want to have those files downloaded to actually do the programming.
All right, cool. Thank you.
Of course. Are any more questions?
I guess what's kind of like our strategy in terms of mass manufacturing C-term?
I think every sub team is kind of in a different place when it comes to manufacturing. If you're asking about couplings in particular, we're gonna start CAM, as you know, and we're gonna finish it up when we get back. But as soon as we finish CAM, we'll have all the materials purchased and we'll just start getting into machining. But there is already a tutorial to do milling on Esprit that I did in the summer, so you guys can definitely check that out to learn Esprit for milling if you want to get started.
Well, I guess I meant more like since there's only so many people who actually know how to do it, like we're learning, but like I don't feel comfortable, for example, like manufacturing a whole piece by myself yet. So is it going to be more like, okay, whoever manufactures first will help then the other people?
Well, yeah, like especially for you, like I'll be there to watch you, so you'll definitely not be doing it like on your own.
Okay.
If that's what your question is. So you'll be learning along the way.
All right, sounds good. Thank you.
Any more questions? Okay. That'll be it then. Thank you for coming, guys. I hope you guys have happy holidays. And I will be posting the video and the slides in general chat. So if you want to refer back to them, go ahead and do that. But thank you so much for coming.
Yep. Thank you, Terence.
Of course.
Thank you. Happy holidays.